Hello, this video will be on lesson 6 on Bayes' theorem. And what this amounts to is working and extending conditional probability to where you can reverse the order in the conditional probability to solve problems. All right, let's take a look at an introductory example here. Suppose we have two containers or urns. One contains two red and three blue marbles. The other has four red and one blue. And we're going to assume that the probability of selecting each urn is 1/2, 50-50. So the probability of selecting a red marble with one selection is basically broken up based on each urn. It's 1/2 times the probability in the first urn, which is 2 out of 5. There's 5 total in the first urn, 2/5. Plus the other option is urn 2, which is also 1/2, and then times the probability of red inside of urn 2, which is 4 out of 5. Totaling that up gives us, with the cancellation here, we're going to get 1/5 plus 2/5, which is equal to 3/5. And so, how did we calculate the probability of red? We looked at the cases there. We could have gotten red from urn 1 or red from urn 2. So it's the probability of urn 1 and red plus the probability of urn 2 and red. Now, recall the conditional probability formula. The probability of A given B is equal to the probability of the intersection of A and B divided by the probability of B. Cross multiplying in this formula gives us that the probability of A given B times the probability of B is equal to the probability of the intersection A and B. So the probability of red is the probability of the intersection U1 and red plus probability U2 and red. Now, substituting back in using this equation gives us the intersection in terms of conditional probability. So, probability of U1 and red, reversing this process here, that's going to give us the probability of red given urn 1 times the probability of urn 1 plus the probability of red given we've selected urn 2 times the probability of U2. And so that's essentially what we did in this formula here. The probability of U1 is 1/2, U2 is 1/2, and then the 2/5, that's the conditional probability. Knowing that you have chosen urn 1, the probability of red is 2/5. Knowing that you've chosen urn 2, the probability of red in that case is 4/5. All right, so a general form. This one's a little bit extreme here. We'll take a look at it. So if we have a sample space broken up into n events, and the events are they form a partition of the sample space, meaning that their union gives us back the whole thing, and there are no overlaps. All these events are mutually exclusive. So the intersection of any of these events is empty. So the probability of event E sub I given A is equal to the probability of E sub I times the reversal there, probability of A given E sub I times the summation of probability E sub K times conditional probability A given E sub K. A is an event in the sample space. So again, we're reversing the condition the conditioning here. So we have that the probability of B given A is the probability of the intersection divided by the probability of the given event A. Cross multiplying, we get probability B given A times probability of A is equal to the probability of the intersection. Now, the probability of the intersection is commutative. The probability of B and A is the same as the probability of A and B. A and B and B and A are the same thing. It's the overlap, the common outcomes of events A and B. So this allows us to get this reversal into the numerator. And so we have here that the probability of E sub I given A using the conditional probability formula, it's the probability of the intersection divided by probability of the given. And then we can use the commutative law there to turn that around there, A and E sub I. So the probability of E sub I given A is equal to probability E sub I times probability of the conditional probability A given E sub I over the sum of those similar terms there, probability E sub k times probability A given E sub k. That denominator is just going to give us back the probability of A, and the numerator is the probability of the intersection. So the numerator is true based on essentially cross multiplying in conditional probability. Now, the denominator here is basically breaking up A into pieces. So we saw that, not a full on proof, but we saw that back up here when we broke up the probability of R into the probability of U1 and R plus the probability of U2 and R, which then became conditional probability forms. So essentially, what we're doing here is expanding out to a situation where you have several urns here, more than two, and you would get this summation type formula in the denominator. And so that is the basic idea between that's the basic idea of how we get this denominator expression. All right, let's take a look at an example. The probability of completing a job on time with and without rain is 0.44 and 0.95 respectively. If the probability of rain is 0.45, what's the probability that the job will be completed on time? So what the question is saying here is, what's the conditional probability that the job will be completed on time? Oh, excuse me, my mistake. The question is asking just for the probability that the job will be completed on time. Now, we know that we are given the conditional probabilities. We're given that the probability that the job is completed on time, given it rained, is 0.44. The probability the job is completed on time, given no rain, is 0.95. We want to find the probability of on time. So we split that up. We could have on time and rain, or we could have on time and no rain. These two expressions there are mutually exclusive, disjoint. Can't have rain and no rain at the same time. And then these each in turn become conditional probabilities here. Probability of on time and rain is the same as probability of on time given rain times the probability of rain. And then for the second one, probably on time given no rain times the probability of no rain. And then we know these pieces here. We know that the conditional probability of on time given rain is 0.44. Probability of rain is 0.45. Plus the probability of on time given no rain is the 0.95. The probability of no rain is 0.55 because the probability of no rain is 1 minus the probability of rain. And then we multiply that out and total it up and get a probability of approximately 0.72. So that's the probability the job will be completed on time. All right. Now, a full on example here. One card out of 52 from a standard deck is lost. From the remaining cards, two cards are drawn and are both hearts. Find the probability the lost card is a heart. So the cases here are that the lost card can be a heart, E1, E2, it could be a club, it could be a spade, or it could be a diamond. So we're exhausting all the different suits here. There are four suits. Notice that E1, E2, E3, E4 satisfy the conditions here of being a partition. Every element of the deck falls into exactly one of these categories. There's no overlap. The probability of selecting any one of these probability of any one of these events selecting a specific suit is 1 out of 4. Let's let E denote the probability of drawing two hearts out of 51. The probability of E given E1. So the probability of drawing two hearts out of 51 given the lost card is a heart. So the lost card is a heart. There are 13 hearts total. We lost one. So it's going to be 12 out of 51 times 11 out of 50. Again, if the lost card is a heart, we only have 12 hearts remaining. And then we take that out, and then we have 11, which we can view as a ratio of combinations or permutations. Now, the probability of E given E2, if the lost card is a club, we have 51 cards left, but we still have all 13 hearts. So that's why, in this case, it's 13 out of 51 times 12 out of 52. And that's going to be the same for the other two situations. E3, again, if we lose a spade, we still have all 13 hearts. If we lose a diamond, we still have all 13 hearts. So the remaining conditional probabilities are all the same, 26 out of 425. So what are we trying to find? We're trying to find the probability that the lost card is a heart, given that the next two cards drawn are both hearts. So in terms of the notation here, we're trying to find the probability lost card is a heart, so that's E1 given E, which is the probability. Actually, it should make a small adjustment here. E should not be probability. E should just be drawing. Let E denote drawing two hearts out of 51. E is an event, and then P of E would be probability. So we're going to find the probability of E1 given E. Lost card is a heart given following two cards were both hearts. Okay. So I know this looks messy here. A lot of these terms are the same. So using Bayes' formula, we reverse the conditioning in the numerator. We have the probability of E given E1 times the probability of E1. We do that same reversal in the denominator, probability of E1 times the probability of E given E1. And then we move on to the other cases with E2, E3, and E4. The probability of E given E1 is 22 out of 425. The probability of E1 is, sorry, let's go back here. E1 was losing a heart, which is 1/4. And then the denominator terms here, notice this first term here is the same as the numerator. the same as the numerator. And then the other three terms are all the same because the probability of each suit is a quarter, and then the probability of E given E2, given E3, given E4, those were all 26 out of 425 right here. Right here. So we can cancel out the 1/4. The 1/4 is common to everything here. And then we can also cancel out the 425, and we're left with 22 over 22 plus 26, 26, 26. Denominator ends up being 100, so we get a perfect 0.22 as our probability. And so what this is telling us here is that knowing that the next two cards were both hearts, what does that tell us? It tells us that it's slightly less likely that the missing card, the lost card, was a heart. If you lost a heart, you'd have a slightly less chance that you got two hearts. A small indication that the missing card was more likely to be something else. All right, a small condensing of the last problem here. We saw a lot of probabilities being the same there. So instead of working by the four suits, we could collapse this down to two situations here. The lost card is either a heart or it's not a heart, any other suit. The probability of losing a heart is 1/4. The probability of losing a different suit is 3/4. Conditional probabilities we worked out. If the lost card is a heart, then we had to multiply by 12. Let me just recopy this here. Yeah, so it was 12 over 51 times 11 over 50. And then in this case, when the lost card is not a heart, then we have the full 13 in the first selection and then 12. And so it simplifies the expression a little bit here in that in your denominator, we're just collapsing and we only have two cases instead of four, but we still get the same answer. All right, let's take a look at another example here. 15 out of 300 freshmen major in math, 25 out of 1,000 sophomores major in math. A math major is chosen at random. Find the probability that they are a freshman. Assume there are equal numbers of freshmen and sophomores. So they're giving us ratios here, they're giving us probabilities. They're not actually telling us the totals here. We're assuming that they're the same. We're saying that 15 out of every 300 freshmen major in math, 25 out of 1,000 sophomores. So those are just rates there. They're not giving us the full totals necessarily there. So we're assuming that there's equal numbers of freshmen and sophomores. So the probability of choosing a freshman is the same as probability of choosing a sophomore, 1/2. Let E denote choosing a math major. So the question is, find the probability of a freshman given a math major is chosen. So that's the probability of E1 given E. So again, we use Bayes' theorem. We reverse the order. Probability E given E1 times the probability of E1. And then we basically have the same kind of setup in the denominator going through the two cases, freshman and sophomore. The idea of the reversal is that this conditional probability should be easier to calculate. The probability of E given E1, that calculation is the probability of choosing a math major given freshman. And so we know that conditional probability. we know that 15 out of 300 freshmen major in math. So that's going to be 15 out of 300. Sorry, let me just move this down here. Okay, so that's 15 out of 300. Probability of E1 was a half. Downstairs, we have the same thing. Then we move on to the sophomores. It was 25 out of every 1,000 math majors, again, times a half. And then you can cancel out the halves, cancel out the 300s, and you can reduce that down. And it turns out to be 2/3. So, given a math major, more likely to be a freshman.